couple of applications of exponential functions, and at this point we're just going to get introduced to these ideas, and until we get a better way of solving exponential equations algebraically when we do logarithms, we're just going to solve these things with a graphing calculator right now. So the first idea that we're going to look at is compound interest. Do you know what compound interest is and how it works? Okay, this is an important idea. Compound interest, say you have some money and you put it in a bank account and your bank account actually pays you interest. That's a little bit hard to find sometimes because most interest rates right now are so low that they don't pay you interest, but we're going to pretend we find one that does. Okay? And we're going to make the interest rates wonderful so that we're really, really excited. Okay? So you've got $1,000. And we're going to find a bank that pays 10% interest. Just allows for our math to work out quite nicely. Now that's probably not realistic. Realistic might be 1% or 2% interest. But what a 10% interest rate means is that after a year, if they were paying you interest once a year, after a year they would give you 10% of 1,000, which is $100, and add $100 to your bank account. And that would be very exciting. But compound interest, the way that it works, is they pick a period on how often they're going to pay you. So if they were paying you once a year, they would give you $100 once. But if they decided to pay you twice a year, compound interest, doesn't mean you're going to get $100 twice, but halfway through the year, you would get 50. You would get half of it. So then, at halfway through the year, you would now have 1,050 in your bank account. And then next 6 months goes by, and are they going to give you 50 again? No. Because now you have more money in your account. What's 10% of 1,050? $105. And in 6 months you get half of that. So now instead of getting $50, you would get half of 105, which is $52.50. And now you have $1,102.50. So if they paid you once a year, you would get $100 at the end of the year, and now have $1,100. If the compounding periods were twice a year, you get a little bit more because you made interest on the interest. And it's compounding. That's why it's called compound interest, because you make interest on the interest. Now, if they decided to pay you every 3 months or 4 times a year, well, now you would get a payment in between here, which would be, well, you'd be supposed to get $100 in a year, but now you're only 3 months have passed, which is 1/4 of a year. So you would get $25 after 3 months. Then after another 3 months, you would get, well, now you have $102.50, so 10% is $102.50. We'd have to divide that by 4. Okay, which would be another $25 and roughly 60 cents. So you've got $1,050 and 60 cents. And then another 3 months would pass, and you would get another $25 and maybe 65 cents. So now you have $1,076, and I'm making up numbers now. I'm not doing the mental math correctly anymore. But then at the end of the year, you get another $25.60, and all of a sudden, ooh, a little bit more. The more times it compounds, the more opportunities you have to make interest on interest. So compound interest works 2 ways. One, if you're investing your money in a bank, they're paying you an interest. You get that interest once a month. Most compounding periods are monthly. And so you are getting paid your interest and then making interest on interest every month. But the same thing happens when you take out a loan. Did anyone buy a car? Does anyone have a car loan yet? Yes? No? Okay. You have a car but no car loan? Whoo! Right? Someone's been selling their math homework. Anyways. And so when you have to pay the bank, they also charge you interest and then charge you interest on the interest as you're going along. So it works both ways. Usually in the bank's favor, that's why they're businesses and they're not out of business. They're making more money than they're giving out. So when you buy a house or buy a car and need to borrow money, you're not only going to pay for what you borrowed, but you're going to pay a lot of interest along the way. So it's important to understand how compound interest works. Now, if we look at the example that they've given, they went for 2%, an investment of $100. Okay? If the compounding period is once a year, they show you that you would get 2%, you would have $102. And after 2 years, you would have that 2% happen twice. Because you would get that 2% happening again. And so what happens is that you're increasing by 1.02, how much you multiplied by the previous year. After 3 years, it would have that 1.02 cubed. What ends up happening is you have an equation where you have your initial amount times a rate to the power of x, how much that rate is continuing. And they've written it here with t instead because they're using t as time. And so if you wanted to figure out how much it was worth after 10 years, you could plug in a 10 for t, and then that would multiply by the 1.02 10 times. When you're having a percentage increase, okay, this is an important thing to look at. Why did they multiply by 1.02? They're showing that if I want a 2% increase, I multiply by 1 to keep the value that I had, and then I add 0.02 to add a little bit more. And putting those together, you could do that all at the same time by multiplying by 1.02. How many of you have done that when figuring out how much tax you have to pay on an item? Right? It costs you $10, or let's say something not as easy mental math, $25, and you want to figure out how much am I going to pay for this in the end. You can do 25 times 1.13, because our taxes are 13%. And by multiplying by 1.13, you'll get the new final cost. It'll do the original plus the 13%. The original is 1 plus 0.13, which is the 13% more. And so you could just multiply it by 1.13 altogether. So they go through this example a little bit more. Compounded semi-annually, and what ends up happening here, you can read, I'll let you look at this. I'm going to show you a formula here that your amount is how much you start with multiplied by 1 plus the interest rate divided by the number of compounding periods to the exponent of time in years and number of compounding periods n. This formula used to be on your formula sheet. It isn't anymore, which temporarily might make you scared that you have to memorize it. But no, they decided not to put any formulas on, and they would give you whatever formula you need in the question. And they'll explain what the formula, everything stands for. So instead of having a few formulas on your formula sheet that you need to know what they were for, now they can give you any formula that they like, and you just have to have the skill to work with any formula if they tell you what it means. All right, and so here it is in the textbook. Those are typically the letters I like to use. They use A0. I use P for principal. That's the amount that you started with. N is the number of compounding periods. T is the time in years. R, or I in this case, is the interest rate as a decimal. And we call the base of the exponent, this part right here, as the growth factor. Because it's bigger than 1, this would draw an exponential graph that has the typical shape of an exponential graph with a vertical stretch in front. What does it mean for us right now? Well, we'll get some questions where we have to use that formula. I'll rewrite the formula for this question. A principal of $1,500 is invested at 4% annual interest, compounded quarterly. To the nearest quarter of a year, when will the amount be $2,500? So the first thing is, if we're giving this formula on an exam, the formula would be there and each of the things would be explained. Okay? So A would be the amount after T years. Have they told us that? Yes. They said it will be 2,500. So we can put in 2,500 for A. P is the principal or the starting amount. They've told us the principal is 1,500, so we can put in 1,500 for P. 1 plus R is the interest rate as a decimal. They gave us the interest rate. We put it in as 0.04. They would tell you that N is the number of compounding periods. This question says that it's compounded quarterly. How many times per year is that? 4 times per year. So then N is 4. This N would be also 4. And the question says, when, to the nearest quarter of a year, when will the amount be 2,500? So it's T that we're wanting to solve for. After writing out the equation, okay, later we'll be able to solve this algebraically. So far, in the examples 1 and 2, the only way we can solve questions with exponents is if the numbers are on our powers chart. Okay? Is 2,500 on your powers chart anywhere? How about 1 plus 0.01? No. So at this point, and we're not going to do a lot of these because they won't test you on these on the final exam, but at this point the only thing we can do is use our graphing calculator. So we can put this equation into y1, this equation into y2. Okay? So in y1, 2,500. In y2, 1,500 bracket 1 plus 0.04 over 4 bracket to the exponent of 4. We don't have a t, so we use x instead. Now when you hit graph, if you're on the standard window, this is what you'll see. Oh, I'm not on the standard window. There's the standard window. Again, we see something similar. So if we can just tell where those two lines intersect, we're fine. What's the problem? We can't see any lines. So we have to have some knowledge of what's happening with our graphs. We have to use our transformations and have some knowledge. First of all, in y1, I have y equals 2,500. That's a horizontal line at 2,500. Did it make sense when I only looked up to 10 that I couldn't see it? And so maybe if I want to see that line, I can go to my window and say my y max has to be bigger than 2,500. Let's do 3,000. Hopefully now I see that horizontal line. Ah. Ooh, and I just by chance and by luck, it looks like my exponential function is coming. It's going to cross in. Oh. So close. So here, I now, by doing that first thing of seeing the one graph, I now see that my x max, I'll have to go beyond 10. Probably 15 would be enough. Graph so fast. And so now that they've intersected, I can calculate that. Second, calculate where do they intersect? Number 5. Enter, enter, enter. At 12, when x is 12.8, to the nearest quarter of a year, 12.83. Is that closer to 12.75? I really don't like rounding to the nearest quarter of a year, right? The actual answer was 12.83. But at 12.75 years, it will be close to 2,500. Not quite 2,500 yet, because we know that it only does that at 12.83 years. Okay, questions 12 and 13.